So we already talked about one of the advantages of heaps over binary search trees. We can get the min or the max depending on what kind of heap that we've actually implemented. We can do that in constant time. Whereas if you had a binary search tree, you would need to do it in log n time because you have to kind of go all the way left in the tree. Now, another advantage of heaps is how we can actually build them. We know that when we have a binary search tree, you have to insert a node every single time to build that binary search tree, and the time complexity of that is n log n, because we have to do n insertions, and to insert each one takes log n time. Now for heaps, you can do it the exact same way. You can keep pushing elements into the heap and it will also take n log n time. But there's actually a special algorithm with heaps, which is sometimes called heapify or just build heap. And the idea is that we could be given some set of values, some list of values, suppose in the format of an array like this. And we can take those values, and they're in no particular order, and we can take them and turn them into a heap that satisfies the properties of a heap, and we can do that in O of n time. Let me show you how. First of all, if we're given an array in this format, it doesn't even satisfy the structure property because we know that we don't really want to have a real value at the 0th index. So the simple thing to do here, since we know these are already in no particular order, let's just take this one and move it to the last position. So at this point with this array, what would our heap look like? It would look exactly like this here. We would have the 50 in the root position, then the 80, then the 40, etc., etc. So we satisfied the structure property pretty easily, but now we have to satisfy the order property. And remember, the order property is recursive. It essentially means that for every single subtree, every node should have a value that's smaller than all of its descendants. So that's what we're going to do. For every single node, we're going to check, does it have a value that's smaller than all of its descendants? And that's because we're doing this for a min heap. For a max heap, you would just do the exact opposite. So we can start at the bottom nodes and then move our way upwards. So we can start at the last node over here. But when we get here, we know it doesn't have any children anyway, so there's no point in doing any kind of comparison here. Same thing for this node, same thing for this node, and this node, and this node. They don't have any children, so we have nothing to compare them with anyway. So that's actually going to be true for half of the nodes. So what I'm saying here is we can actually just skip all of these if we want to. I mean, we could start at the end and, run the algorithm like that, but there's no need to. So to be a little bit smarter, we can just skip half of these. How would we do that in terms of code? Well, we can get the number of nodes in the heap, which is not necessarily the number of nodes in the array because we know we have a dummy. So we would take the length, which in this case would be 10 minus 1, which would give us 9 because we know there's 9 actual nodes here. And then we would take that and divide it by 2. So 9 divided by 2, rounding down, of course, would lead us to be at index 4. So 30 is the first node that actually has children. Taking a look at our picture, that is definitely true. If you don't end up remembering a fact like this, it's okay to still start at the end and then go backwards anyway. It shouldn't change the overall time complexity, but this is how it's taught in most courses. So we already know that all of these subtrees are valid. They don't even have any children anyway, but now moving to 30, let's check, is 30 valid? Is it smaller than all of its children? Well, it has 2 children, it's smaller than 90, and it's smaller than 60, so we don't have to do anything. Notice how what we're actually doing here is the same percolating down algorithm that we talked about earlier when we were removing nodes. This is the exact same thing. What we're doing here essentially is going through every single node that has children and percolating down if it can be moved down. So we did it for 30. We didn't need to, perform any swaps. Now let's move to the next one, 40. Take a look. Let's compare it. First, does it have 2 children? Yes, it does. Is the right child smaller than the left child? Yes, it is. Is the right child smaller than the parent? Yes, it is. So we swap it with the right child. So now that we've done that, we already knew this subtree was a valid heap. This subtree was a valid heap. Now we know this entire subtree is also a valid heap. Now let's move to the left. We get to 80. That's this node over here. Does 80 have 2 children? Yes, it does. Is the right child smaller? Yes, it is. So if we're going to swap 80 with something, it would probably be this one. So let's compare these two together. Is 10 smaller than 80? Yes, it is. So let's swap 80 with this node over here. So originally we already knew this subtree was valid and this subtree was valid. Now we know that we've percolated down for this, that this entire thing is valid. Now, when we are percolating down, we are going to keep percolating down, but at this point, this one doesn't have any children anyway, so there's nothing for us to do. Now we get to the last node in our array. Well, the first node actually, 50. It's the root. So time to percolate. Let's compare the two children together. Which one of them is smaller? 10 is smaller. So if we're going to swap 50 with anything, it's probably going to be this one. Let's compare 50 to 10. Is 10 smaller than 50? Yes, it is. So let's swap these two now. It's definitely starting to get a bit messy now, but let's try to continue. We're almost done. We're at the 50 now. We're continuing to percolate this down. Let's compare the two children together because we have two children. Which one of them is smaller? 30 is smaller. So let's compare 50 with the smaller child, 30. Is 50 bigger than 30? Yes, it is. So let's swap them. And at this point, I'm not even going to be maintaining this array because I think it's getting too complicated. But you get the idea that anytime we perform swaps here, under the hood, there's an actual array that's maintaining all of that. So the 30 is now going to be over here, and the 50 is going to be over here. Now continuing to percolate this, let's check. We have two children still. Let's compare the two children. This one is smaller. Now let's compare that smaller child with 50. Is 50 bigger than 60? Nope. So 50 can stay exactly where it is. We found the correct spot to put the 50. So now at this point, this is what our heap would look like. And tell me, does it look valid to you or not? Well, it's a little bit hard to read because it's gotten messy, but the smallest value is in the root. 20 is smaller than all of its descendants. 30 is smaller than all of its descendants. 50 is smaller than all of its descendants. 80 doesn't have any descendants, and the rest of these nodes don't have any descendants either. So we definitely were able to do this. Now let's take a quick look at the code. So the heapify algorithm is pretty similar to remove that we talked about earlier, only in this case, heapify, or build heap you could call it, is going to be passed in some input array. And when we have that input array, we're basically going to take the 0th element and move it to the last position. That's what append is doing. It's basically pushing it to the end. And then we're just assigning that array to be our heap. We know it satisfies the structure property. Now it's time to satisfy the order property. We have a current index. We basically take the length of the heap, subtract 1, and then divide it by 2, just like I talked about earlier. This is integer division in Python. It'll round down, but most languages will round down by default. And current is going to be at this point, just like we showed in the walkthrough. And then we're going to have another copy of current. We're going to call it I, and at that point, we're just doing the exact same percolate down algorithm I talked about earlier when we were doing removing or popping from the heap. So I won't go super into detail. It'll be the exact same idea. But after we've percolated this down, in this case, we wouldn't actually do any swaps, we're going to be done with this while loop, and then we're going to take our current index and subtract by 1. Because remember, we're going in reverse order. We're going to go to this node, and then we're going to go to this node, and then we're going to go to this node. And for each of these, we're going to percolate them down if we can. Now, if you were actually implementing your own class for a heap, you'd probably put this in like a helper function since it's being used not only here, but it's also being used in heap pop. So you could probably just put this in a helper function. The reason I wrote this out explicitly is just to kind of show you exactly what is going on with the heapify algorithm. Now, why is this heapify algorithm a linear time algorithm? Because at first glance, it seems to be an n log n algorithm because we're going through pretty much every node in the tree and having to percolate it down. Percolating down might be a log n operation, let's say. So why is the big O time complexity big O of n? Well, first of all, I'll just say that you're probably never going to have to prove this or even argue that it is a linear time algorithm. Just knowing it is enough. But I'll quickly go over the general intuition of why it's the case. First of all, if we had to take every node and percolate it up, or if we had to take every node and percolate it down, which one would we rather do? Which one seems more efficient? Well, if we're percolating down, then only the root node actually has to go through the whole height of the tree. And then these two have to go to the whole height minus 1. And then a bunch of nodes here go an even smaller distance. And we get more and more nodes as we go down. Because remember, this is a complete binary tree. But if we're percolating up, it's worse because now we have a bunch of nodes that have to go the whole height of the tree. And then we have a smaller amount of nodes that have to go the whole height minus 1. So percolating down is going to be more efficient. When we get to the root node, we just have a single node here that doesn't have to be percolated up. Whereas if we percolate down, we have a bunch of nodes that don't have to be percolated down. So shifting these down is generally going to be more efficient if we have to do it for all of the nodes. Now let's say n is the total number of nodes in the tree. And let's say in this case, we actually had a full binary tree just to make the math a little bit more simple. We know that roughly half of the nodes are going to be in the last level. Right, that's kind of something we talked about earlier in the course, right? This is going to be 1, 2, 4, 8. Each term is going to be roughly equal to all the previous terms combined. Let's say we have roughly n divided by 2 nodes in the last level. Now for each of these nodes, how much are we going to have to percolate them down? Well, remember, the last level doesn't need to be percolated at all. So we get a 0 times n divided by 2. What about the next level? Well, that's going to have half of the nodes that this level had. So we can call that n divided by 4. How much are we going to have to percolate these down? Well, 1 each. So we're adding these two terms together. 0 times n divided by 2 and 1 times n divided by 4. And if we expand that, we get a summation that looks like this. Now the number of terms that we're going to be adding together is going to be roughly equal to the height of the tree. So if you remember your math, we'll get something like this, but at this point you probably don't care. And this would roughly evaluate to n. So we know that the big O time complexity of this is indeed big O of n. You won't have to memorize this, don't worry. And you most likely don't care about it either. I just wanted to mention it for the sake of completeness. But the important thing here is that just because we can be given some random n elements and then turn that into a heap doesn't mean we can actually sort all of them in O of n time. Because just because we have a heap, if we wanted to turn that heap now into a sorted array, we first built the heap in O of n time, but then we'd have to pop every single element in the heap. We know popping is still going to be a log n time operation. If we have to do it for n elements, then it'll take n log n. So what I'm saying here is we can actually use heaps also to sort values, and we can do that also in n log n time, just like binary trees, just like merge sort, and the rest. So this is yet another example of sorting. So we talked about some of the advantages of heaps over binary search trees. We can get the min and max in constant time. We can heapify, we can build the heap in O of n time. But the downside of heaps is that we can't just search for a random element and then do that in log n time like we can with BSTs. With a heap, suppose we're looking for the value 30. We get to the root node, we're at 14. It's not 30. Well, we know all values in the right subtree are greater than 14, and we know all values in the left subtree are greater than 14. So the 30 could be in both subtrees. It could be here or it could be there. We don't know where it is. We haven't narrowed it down. So to search for an element, we'd have to go through every single node in the tree. That would be an O of n time operation, but with binary search trees, it's log n. So binary heaps are not good for searching, but that's okay because they're not intended for that. They're intended to get the priority element, which is either the min or the max. And the last thing I want to mention about heaps is that when it comes to coding interviews, you actually have to use a heap more often than you have to use a binary search tree. At least I'm talking about like a built-in data structure where the data structure is a part of the solution. BST problems are also common, but it's usually you're implementing a part of the BST. You're searching for something, you're calculating something. But when it comes to problems where you actually have to use the data structure as like a utility data structure, it's pretty rare that you end up actually needing binary search trees. It's more often that you need a heap, because it's more often that you need like a minimum or maximum value. You need to continue doing that. There are a ton of algorithms where heaps are really important. So it's a very good data structure to understand. You should at the very least understand that heapify runs in linear time, and you can push and pop from the heap in log n time, and you can get the min or the max depending on what type of heap you have in constant time. Those are all important to know, even if you don't necessarily remember how to implement all of them.